Perfect. Okay. Um, I am going to kind of, if you can still see my pretty face on the screen, you might see me looking off to the right. I set this up on dual screens here. So anyway, this is going to be kind of a brief overview. I mean, I've done 4-hour presentations just on a single one of these tests before. So we're not going to get down into those type of weeds, and I do apologize for some of you attending today. Maybe you've heard some of this, maybe you know some of this. The goal here is to do an introduction and not kind of blow everybody out of the water here. So, but feel free to ask, complex questions if you have them. So the first thing is I try to lay a little bit of groundwork and say, okay, we need to understand and consider that soil is a living ecosystem. Now, this may sound kind of funny to some of you sitting here today because you're like, yeah, we've known this. That's how we already think. But for the vast majority of people, especially those not directly connected to ag, they don't think of soil as an ecosystem. They typically don't even call it soil, they call it dirt, and it's a growing medium. And that is typically what people see it as. However, the soil is the basis for most of the nutrient cycling that takes place to feed your crops, to feed your plants, which ultimately feed us and your animals. This nutrient cycling goes through organic matter pools. This influences, I have nitrogen and phosphorus and carbon availability, but it's all the nutrients. And most of this is driven through predation. So microbes in the soil, that's hard because we can't see them, but the microbes in the soil are consuming each other. And as they consume things, and each other, that's where nutrient cycling happens. So in other words, we eat food and we cycle nutrients through our body, and then the nutrients leave our body as manure and urine. And ultimately, when we die, the nutrients return to the soil to start that cycle over again. We live, hopefully, for 80, 90, 100 years, but microbes live for a couple of weeks. And that's if they're not being eaten by something else. This process also, soil aggregation. So soil structure is built through microorganisms. Glomalin, you're going to see a lot of fancy words, but glomalin and fungal hyphae, those are essentially the glues that hold the particles together in the soil. So your soil is made up of sand, silts, and clays, and those are glued together through biological metabolites or waste products. This is important as it increases the stability of your soil. It helps hold your soil where it needs to be. It increases pore structure, which allows for rooting depth. This is the interaction phase between the soil and the plant. On top of that, it increases water holding capacity. Honestly, I know that there's a lot of focus in agriculture talking about providing enough food to feed a growing population, right? And to feed the world. That's been a message carrying that torch in agriculture for the last 40 or 50 years. I would argue that we will fight over water long before we fight over food. The water cycles are completely broken, and getting water into the soil is the first step. There's also a number of interactions that take place, plant microbe interactions, and we call those symbioses. Some of these, the ones that we have focused on in agriculture, are usually the negative ones. So disease, parasites, those are still symbioses in some way. But those are negative interactions. Whereas the mutually beneficial ones are the ones where we have rhizobiums and legumes to help fix nitrogen, mycorrhizal fungi and plant roots to help with nutrient transport and disease, et cetera, et cetera. So I see there's a comment here in the chat really quick. Will you be able to get a copy of the slide deck? Yeah, I have no problem doing that. So I'll provide that to Felicia after after the presentation. So we have these different physical, chemical, and biological components of the soil, and where these interact, everyone's probably seen this, dendrogram, you've got physical, chemical, and biological, and where these overlap, this is where we generally talk about soil health, the interactions of these three things, and how do we manage those things. From the world of soil testing, this is what that kind of looks like. And unfortunately, this isn't even a comprehensive list, but if you look at things like soil texture in the upper left-hand side, soil structure, those are measures of physical soil parameters. Of course, down below in biological, we have soil biodiversity, organic carbon pools, microbial biomass. To this point, especially in commercial soil testing, most of the focus has been on the chemical side. Right? Reactions, cation exchange capacity, or CEC, nutrient reserves, balancing of ratios, etc. And then you have all these areas where they kind of intertwine, and you've got some that kind of answer both questions or two of the three. But what we really want to do is say, look, if somebody were to send me a soil sample, and this happens a lot, and they say, run whatever you think, can you imagine what your soil test bill would be if we ran all these things? This is why it's important to understand what your resource concerns are. So for example, if you are in a heavy soil texture and you are irrigating your crop, one of your concerns may be irrigation efficiency. It's important to look at water infiltration, water holding capacity of your soil. In other words, if your soil can hold 1 inch of water in the top foot, there's no reason to put on 2 inches of water. Not only does it cost you money, it's a waste of that resource, for example. So those are the types of tests. Now, on the next few slides, I'm going to step through some of these individual tests, and we'll address physical, chemical, and biological in different aspects. And so this is always fun. The very first test I talked about is not a soil test at all. It's cover crop test. And the reason I put this up here is because most people who use cover crops or employ cover crops are doing so to make the soil better, to try to fix the soil and help the biological part. However, one of the largest complaints or concerns with cover crops is that it's an added expense. So on the short term, before you get these long-term benefits, originally they say, well, what am I supposed to do to cover the $30 per acre or $40 per acre? Where's the benefit? Well, obviously, if you were in a grazing system, then that's a lot easier to answer. If you are in a row crop situation, that can be a little more difficult. And yes, there's a lot of indirect benefits, insects, etc. But with this test, we're going to show you how you can put numbers to your cover crop. I can go to the next slide. So generally how you sample this, because I get asked this question all the time. So in this example, I said, a 3 foot by 3 foot area. So if you've got really tall, thick cover crops, it may be a 2 foot by 2 foot area or less. But you clip off all the plant material above ground, and you literally cram all of that material into a trash bin. It doesn't matter if you mash it up, it doesn't make any difference. When you send that to the lab, what we will do is get a wet weight. We will dry the sample in its entirety and get a dry weight and determine moisture. When we're able to determine the moisture, we calculate dry matter. What that provides to you is this report, and I'm going to focus on the upper right-hand side so you can see the wet weight and then percent dry matter. When we know the area that you sampled, we're able to tell you that you have X number of tons of dry matter per acre. So now you have the biomass of what did your cover crop produce, okay? Below that, just below that, we have a carbon to nitrogen ratio. Anytime you talk about soil health or cover crops, this carbon to nitrogen ratio comes up in that conversation. So knowing the carbon to nitrogen ratio tells us a little bit about how fast potentially that cover crop can break down. Below that, though, what are you getting back from the breakdown of your cover crop? In other words, what's being released, what's being cycled through the biology back to the soil? So down below, we have carbon on this example. You have 4,000, almost 600 pounds of carbon per acre, 160 pounds of nitrogen in that above ground biomass of that cover crop. This is a real example, by the way. It was actually reported on the 25th of October a year ago. You've got 60 pounds roughly of phosphorus, 300 pounds of potassium. So if you're sitting there thinking, okay, I know what the price of fertilizer is, you can start to monetize credits from your cover crop. This is active nutrients that are not tied up in your soil. They're not locked away. They're tied up in your cover crop biomass, but the microbes then help release that, right? So for the people using cover crops, this is a pretty powerful metric because the old way of doing this was, I called it the one-eye test. And it's where you would drive down the road next to your field and you'd close your one good eye and you'd look at the cover crop and say, well, it's about yay tall and it's pretty thick. I think I've got about 60 pounds of nitrogen in that cover crop, you know, based on whatever you planted, right? It was literally just guessing. This puts some numbers to it, and it's relatively cheap. So it can add value. We've got several farmers that are monetizing their cover crop to show just how valuable they are and what they're getting back. I focused in on these. These are the big ones here. So a lot of people monetize carbon, right? We've all heard of carbon markets, the importance of carbon, carbon credits, etc. Even if you forget the markets. The reason there's a market there is because carbon is important, but it's important for your operation, even without the credits. It's what drives everything in the system. And a lot of people tell me, well, I'm going to buy this product to put on carbon, right? Whether it's molasses or compost or whatever it may be. There is no economically viable option better than cover crops to capture carbon. Plants are designed to do just that. So that number is usually a big number, and you can monetize that. 2.5 tons here. The nitrogen, again, obviously an easy one to monetize as nitrogen fertilizer is used extensively. I see we have a question really quick from Jim. I may be getting ahead of you, but how much of the N in the cover crop test do we assume we're losing to the atmosphere? Great question, Jim. And no, you're not ahead of yourself. So the way we credit this, it's still, let me back up one slide here. Look, it's still a guess. I mean, the number here is not a guess. This is what's in your cover crop. How we credit that is still a guess. Now, that may not seem reassuring to anybody, but here's what we look at. What is the carbon to nitrogen ratio of your cover crop? The lower the ratio, the faster that cover crop will break down. All other things considered, right? I mean, if you've got two cover crops in the same field next to each other, same climate, right? Same soil type, same biology level, the one with the lower seed-in ratio will break down faster. We know this, soybeans break down faster than corn. So that's the first thing. The second thing is that if you are running a Haney test, which we'll discuss here in a little bit, if you're running a Haney test, then we look at the soil respiration as an indicator of microbial activity. The higher that activity, the higher we will assume the cover crop will break down, and we give you a larger credit from that. The third thing that we look at, of course, is climate and management. So if you tell me that you're in the desert Southwest and it's dry and hot, your residue decomposition is going to be slower than someplace like Georgia, warm and wet, or hot and wet. Of course, if you tell me, well, I'm in the desert, but I'm irrigating, well, then now we're going to look at it more like Georgia. If very little of the nitrogen in this crop is going to be lost to the atmosphere. And the reason for that is the nitrogen we're measuring here is protein. It's not nitrate, it's not ammonium. So it is bound to carbon, and the microbes, just like you and I, they don't want to eat nitrate. If they don't have to, they want to eat steak. They want to eat protein. And matter of fact, if we eat nitrate, it kills us, right? So very little is lost. The biggest potential risk of loss is that if this decomposition system was happening and you had 3 inches of rain every day for 4 or 5 days, and now your soils are waterlogged, everything is wet, and it goes anaerobic. And if it goes anaerobic, then the microbes will use nitrogen in place of oxygen, and they will create nitrous oxide gas. And then that is we call that volatilization. And it's the same process that happens with nitrogen fertilizers being put on wet soils in the fall, and if they go anaerobic, same process. Otherwise, very little of it's lost, especially if you're terminating your cover crop and then planting a cash crop behind it, because any cycling that's coming out of that system, nitrate and ammonium at the very end of the cycling system from the protein, gets taken up by the next crop almost immediately. So that's mimicking more of a native system in that situation. Hope that helps. So I'm going to jump into PLFA, and I see it's already been 20 minutes, and so I'm going to have to zoom through some of this, Felicia. PLFA. PLFA is just a big, nice, long, or short acronym for the nice long-term phospholipid fatty acids. So we use this test to categorize or look at the microbial community. All living organisms are made up of cells, and all of those cells contain a membrane, and within that cell membrane are fats, fatty acids. So we are stripping all the fats out of the cell membranes. Yes, we are killing all the microbes in this situation. What's nice, though, is that we can actually quantify those. So this is a quantifiable test, and it represents living biomass. So when a microbe dies, these fatty acids get consumed by other microbes, which means they don't stick around in the soil for very long. That allows us to look at the influence of environment and land management on microbial biomass. Now, environment is not something that you get to decide. Obviously, you are where you are, but you can influence environment on the scale of microorganisms. In other words, bare soil versus covered soil. What's the temperature in July of those two soils? You don't control the temperature outside. You're not going to stop the sun from rising, etc. But you can change the environment at the soil surface based on management. So inside a bacterial membrane, we've got all of this stuff. And if we strip all that stuff away, we're left with this. So this is your lipids, fats. This is your fatty acid layer. And this is what we're focusing on in the analysis. The little pinkish purple circles, those are phosphate groups. So those are phosphorus. It's the same phosphorus that your plants require. The microbes require it as well. The little aquamarine or blue squiggly lines, those are your fatty acid tails. Fats are made up of carbon, hydrogen, and oxygen. And what this does is it keeps the outside of the cell out and the inside of the cell in. It's the reason why when you put water on your skin, it doesn't just soak all in and immediately, and why you don't just lose all the water in your body. Cell membranes work for this. So when we get back numbers, how do we understand it? I'll show you a report, but how do we look at this? Well, there's a couple of things. We like biomass, right, as an indicator of soil health. The more life your soil can support from a microbial standpoint, generally the healthier it is. But diversity is incredibly important, and it is the number one metric from this test. The reason diversity is so important is because different microbes carry different functions. Some of them are very good at mobilizing phosphorus, some of them are great at fixing nitrogen, but very few, if any, microbes contain all of the tools in their toolbox to provide all the services, from disease suppression to plant root growth promotion, etc. So diversity, much like a community of people, is important because you need different skill sets all coming together to have a functioning community with good outcome. I always joke around that if you had a community of people with 5,000 of you and they were all lawyers, it'd be a really terrible place to live, right? So diversity is important. Biomass is secondarily important. Unfortunately, there is no standard ranking established. What should this number be, right? Well, given your management and your climate and all of those things, well, those numbers don't exist. So what we've done is I've processed nearly 75,000 of these at this point. We built tables. And so on this table, on the very left, and it's a table ranking both of these metrics together. So the way this works is, let's say your biomass is 1,300. So that falls in the slightly below average category for biomass, but your diversity is 1.45. So the way that works is biomass numbers on the left, diversity number on the right. If your diversity is 1.45, that's good. That's in the good category. Since diversity is more important than biomass, and these are weighted, we would say that your soil overall is slightly above average from a microbial standpoint. And so that's how we look at this. There are some other ratios on this report. There are 7 of them. The ratios here that you see, are fungal to bacterial, predator to prey, which is your protozoans versus bacteria. Protozoans graze on bacteria. And then you see gram positive and gram negative. Those are your 3 main ones. The other ones are really more for researchers. And I do see the question here, optimum C to N. I'll jump into that real quick right after this. The gram positive to gram negative, it doesn't mean good versus bad. It has to do with the cell structure of the microbes, and we won't really get into that. But gram positive and negative are influenced by environment because they're built differently. So they handle different environmental stressors differently. And so we use their ratio to look and say, hey, is your soil too hot? Is it too dry? Did we have a fertilizer spill or a chemical spill in a spot? Those types of things is what we look at with that. The question posed here in the chat, is there an optimum C to N, and does increased cycling always mean better soil health, better results, or can it end up leaving your soil bare? For example, broken down too fast. So I'm going to address the second part of that question. You are exactly correct. Cycling faster is not always better. For 95% of the soils that we've dealt with and seen, the issue is trying to get stuff to break down faster, because that's where most people are. But you're right, we have several growers that the goal is to slow down decomposition because we don't want to leave bare soil. So how does that influence the C to N ratio? Think of it like starting a fire. you start off with things like lighter fluid and, little sticks and shavings, because those will combust and burn faster. In the case of cover crops, those are brassicas and legumes. So if your residue is not disappearing very fast, if you can see that happening, increase the amount of brassicas and legumes in your mix or in your rotation, and that will help jumpstart the system and get it burning, get it going. However, as you build that fire and as you build that biology and it's breaking things down, we have to start transitioning from sticks and lighter fluid to more substantial fuel sources, right? Now you're doing logs, and pretty soon you're putting on more logs and bigger logs and those things to keep that fire burning. So the optimal seed-in ratio typically is anywhere from 25-1 up to about 40-1. With most people generally agreeing the optimal place to start is around 30-1. But again, if at 30-1, your residue, you're out harvesting your corn and you've still got all the residue sitting there from when you terminated your cover crop, then we need to back off on the carbon crops, the grasses in the mix, and add in brassicas and legumes, and vice versa. That's a good question. So this is a breakdown of the PLFA report. I mentioned the ratios and things like that. So really quickly, we'll see here total microbial biomass followed by functional group diversity index. We do rank the fungi to bacteria ratio, predator to prey, or protozoa and bacteria, and gram positive and gram negative. And then we take those 5 numbers and give you an overall ranking. And each of these are weighted. So I mentioned diversity is about 50% of that score. Microbial biomass is around 30%. Fungi to bacteria is 15%, and then protozoa and bacteria is 5%, and the gram positive, gram negative is almost negligible in that overall ranking. Then, sorry, I thought we had a chat. So any questions on PLFA? I know that's a bird's eye view, but I got a lot to kind of get through and cover. Again, PLFA is a microbial community analysis. So let me actually step back really quick. We're looking for total bacteria, total fungi, protozoans. We're able to break those down into some groups. So what this is good for is a report card of your management. What PLFA does not work well for is if you ask me, do I specifically have this disease as a microbe? Or do I have these nitrogen fixers? The PLFA will not tell us species. It doesn't get to that level. So that's why we call this a functional group diversity index, not a species index, diversity index. If you really want to know species, the new technologies that are out there now, we're running one of them, the Biomaker's bee crop test. It's a genomics test. I'm not going to cover it in here. It's incredibly complex, but it's like PLFA, but I would say, but on steroids. Like, it will give you species names and a lot of that. Very little reason to run both. The difference is that if you need a NASCAR, you got to own a NASCAR. If you don't need a NASCAR, it's a giant waste of money to have one to go pick up groceries, right? So again, understanding what your goals are with the testing will kind of tell you what direction to go there. So with that, I'm going to jump into a physical measure, aggregate stability. This is a real important one, and it's something that's relatively new in the world of commercial testing. It's gained a lot of attention and focus. I mentioned before that your soil is made up of different particles of various sizes. So just gravel is not one of those primary particles, but it's in this diagram to show you the size comparison. So, in millimeters, gravel is up to about 2 millimeters in size. Sand is around 1 millimeter in size. Silt is microns, thousandths of a millimeter, and clay is invisible at this scale, to give you an idea of just how small some of these particles are. And those particles join together to give us different structure complexes of soil. So we have granular, which is kind of what is desirable. That's what everyone is shooting for. Some people describe it as chocolate cake, or cottage cheese. Hopefully your cottage cheese doesn't look that color, but this is what we're shooting for. Blocky is what we would consider to be almost like small dirt clods. Dirt clods are not soil structure; those are man-made. Platy is where we see this a lot in the A to B horizon, especially with tillage. We have those hard pans, and those are plate structures, and it's where the sand, silts, and clays have separated and settled. Massive structure. This is simply large dirt clods, baseballs, softballs, that type of thing. Single grain, that is where we have pulverized the soil to a point where it's dry and we've reduced it. This is the dust. This is what we see when we've got dry, windy conditions and tillage happening or bare soil, and we see single grain blow. If you add water to single grain, that's where you develop the other three: blocky, massive, and platy, depending on your soil texture. So how do we build aggregates? This slide, I love this diagram, but it's laid out backwards. Sorry, we had a different question. How often do you recommend doing PLFA tests? Generally, for PLFA, it's once prior to changing management, to establish a baseline. And then depending on the intensity of that management change, no more than once a year. But generally every 2 or 3 years. Try to sample at the same time, right? Don't pull a sample in March and then pull one in October, unless your goal is to compare the difference between March and October. Like, we want to be in the same general growth phases for the microbes. If you're doing treatments of product, treated versus untreated, then we're going to sample both areas prior to treatment. You're going to put your treatment on this area, and then you're going to wait generally 2 to 3 months for most products, and you're going to come back and sample both of those again. So now you have a baseline comparison, and now you've got a treatment, untreated, and then a comparison in 3 months. The reason you don't just sample the treated is because temperature, moisture, and all those other factors could make it look better or worse. So you need to have that negative control in that treatment. Another question: some research was done taking monthly samples and showing large fluctuations in results within month to month, particularly for biology. With this in mind, how often should testing be done? Baseline and then every year at the same time. Yes, so you are right. Biology should change. It's going to change. It's very different than just pH and soil organic matter and those things. So yes, do not sample every month. We understand that it's variable. It's going to be variable. It's the same reason why when you go to the doctor and you're going to have blood work done, they tell you, okay, don't eat anything, right? Fast. We're trying to mitigate all those variables. So depth of sample is important. If you choose to do a 6-inch depth, 0 to 6 inches, make sure we stay at 0 to 6 and we don't change to 8 the next year. The same general time of year, absolutely. Same general conditions, spring versus fall. That doesn't mean it's just a day. It's like, say, well, on May 15th, I'm going to sample, because May 15th here this last year was 45 degrees. But 2 years prior to that, it was 104 degrees. It had been. So you shift within those seasons. But that's a very good question. Yes, they are variable. They're variable because they should be. If your soil's alive, it should be changing. It creates issues, but at the same time, it's not all bad. We just got to take it in context. So on aggregate formation, this slide actually starts on the right. So primary particles, I mentioned, are joined together with humus, microbial debris, etc. And when that happens, we create what's called a sub-micro aggregate. The size of these aggregates around 0.03 millimeters up to 0.1 millimeter. Those sub-micro aggregates are then glued together to make micro aggregates with the use of root hairs, fungal hyphae, and the fancy term polysaccharides, just meaning mini sugars. So sugar molecules that are produced by microbes help glue this together. Finally, the micro aggregates are joined together to make a macro aggregate. So through this process, the microbes are building their house. And they're using the plants and working with the plants to do that. And this is important for the plants because it creates gas exchange, which is a passive process. So your soil exhales CO2 and it inhales oxygen, and plant roots will not grow where there's not oxygen and water. And so this is really important. Now, I used to think that tillage is what destroyed soil aggregates. Tillage speeds up the degradation of soil aggregates. But if you think about the size of an aggregate, a macro aggregate is 1/4 of a millimeter. Your disc blades or the plow or whatever you're using is not sharp enough to cut those aggregates. So physically, it's not breaking them up. Microbes are continuously building and breaking down soil aggregates. This happens on about a 3-week timeline. That does not mean that your soil builds all the aggregates and then 3 weeks later, all the aggregates fall apart. It's continuum. So they're constantly being built, they're constantly being broken down. I tell people, if you've ever remodeled your house or built anything, it requires a little bit of destruction to remodel your kitchen. However, you have to be able to get the resources available to rebuild the kitchen. Those resources, in this case, come from the plant. They come from the residue. If your soil's bare, that is like all the stores being closed. And that's COVID all over again. Nothing's on the shelf. You can't find anything. So they're doing the destruction part and they can't rebuild. And when that happens over the course of 7 or 8 months between growing seasons, the soil system starts to collapse. And that's where we start to get soil crusting, hard pans, et cetera, et cetera. Even 30-year no-till operations exhibit really hard soil. And people say to me, well, I shouldn't have compaction. I haven't tilled the soil in 30 years. However, you're still doing corn and beans in my part of the world, corn and beans with nothing in between, narrow rotation, putting on lots of nitrogen fertilizer every other year. And the microbes use all of that to access carbon from the soil organic matter. And remember, carbon's what holds this stuff together. So when they eat it, now you've got a house built with bricks, but no mortar. And then the wind blows and it rains, and guess what? Your bricks fall apart and they turn into a pile, right? And so that's what's happening in that soil system. Aggregation and carbon content lead directly into water holding capacity. So water holding capacity, as the name would imply, is how much water can your soil hold? Well, your soil is this number is primarily influenced by texture. So on the left-hand side, we have sand. We all know that sand infiltrates water, but it doesn't hold it very well. And on the right-hand side, we have clay. We all know that clay holds water really, really well if you can get it wet. So what we have on the very top line is what is called field capacity. And then field capacity is essentially the amount of water your soil can hold after gravimetric water is taken off. So it's saturated to a field capacity point. In between field capacity and wilting point is what we call easily available water and slowly available water, collectively just plant available water. Wilting point is the amount you get to a certain point where the soil can hold the water tighter more closely than the plant roots can take water in. It's a tug of war. And the soil wins at the wilting point. So this is why some soil textures, heavy clay soils, can appear to be wet or can have moisture in it, but your crops exhibit drought stress. It's because of this high wilting point of clay soils. So we can measure this and determine this, and you can influence this. Now you can't you can't make a sand into a clay, right? You can't take a Ford Pinto and turn it into that NASCAR we mentioned earlier. There's limitations to what can be done, but within these textural classes, you can influence the water holding capacity based on carbon content. So as you increase soil organic matter and as you keep the ground covered and reduce evaporation and increase all of these things, so does your available water. So this is a slow one. I'll answer this question now. How often do you sample for this? Once every 3 to 5 years. This is not something that's going to change dramatically overnight. Even with aggregate stability, yes, it changes rapidly. The microbes change it rapidly. But again, a baseline, and then at the absolute most, once every year. Generally, though, kind of like PLFA, every 2 to 3 years is really more likely. We're looking for differences over time, not necessarily differences over time within a period of weeks. We're looking for trends, right, up or down. I got 2 more to go here. The total nutrient digest. This is a really important one. It's a little different. A lot of people love this test. As its name would imply, we are measuring the total amount of nutrients in your soil. So usually when you send a soil sample to a lab and ask for phosphorus or nitrate or potassium, what the lab does is it adds different chemistry to the soil to extract those nutrients. Those extractions are supposed to be showing you what is available to the plant. The total nutrient digest, however, is telling you all the nitrogen, all the phosphorus, so available and unavailable in the plant, or sorry, in the soil, excuse me. In other words, think of this like evaluating your net wealth. So total nutrient digest is saying your total net wealth is this for carbon. Whereas other soil tests are like measuring your checking account. So in this example, this blows people away usually because I hear this all the time. I don't have any phosphorus. My soil test told me I've got 20 pounds of phosphorus in my soil. And my agronomist, the fertilizer company, whoever told me that if I don't buy the phosphorus from them, that I don't have any. And I am going to show you that you probably have 10 times or 100 times more than what you thought you had. Then the question is, well, what good does that do me? What good does it do you to have $50 million that you can't touch? Well, you can touch it through the microbes. The microorganisms are the ones that contain the tools, the enzymes, and everything to move this quote unquote fixed asset of potassium or phosphorus into an asset that you can use. In other words, it's interest. This is your principal, and you're going to live off the interest. For example, how many of you have ever seen a tree growing out of the side of a mountain? You know, the rock. Well, where did the tree get any of those nutrients? Because I doubt somebody climbed up there with a 5-gallon bucket full of dry fertilizer and spread it on the side of that rock. Well, the nutrients are contained in the rock. And most trees, especially coniferous trees, pine trees, form very tight associations with mycorrhizal fungi. The mycorrhizal fungi produce enzymes that will bore through rock. And as they break down the rock, the plant roots follow in those channels. And when the plant provides the carbon, that's the part the microbe's missing, it provides the carbon, and where the carbon meets the nutrients, we create soil. So that is how we go from rock and gravel to dirt to soil. Your soil still contains a lot of the remnants of those nutrients, and that's what this test is measuring. On this example here, we see that we have nearly 61,000 pounds of carbon per acre, 5,300 pounds of nitrogen, 2,300 pounds of phosphorus, and this is in the top 6 inches, by the way. So for this example, it's a 6-inch sample. Now, the fertilizer equivalent, that is something that I put on there and calculated to show you what it would take if you were to buy fertilizer to equal these nutrient contents. So nitrogen, for example, 5,300 pounds in your soil. If you wanted to purchase 5,300 pounds of nitrogen as urea, 46% nitrogen per pound, you would need 11,530 pounds of nitrogen as urea to get 5,300 pounds of nitrogen. So these are here just to show you what the value truly is of the nutrients in your crop. Is there a healthy range of nutrients based on soil type? So that's a great question. By and large, the answer is not yes or no. I mean, it really depends on what you're trying to grow. And also for the most part, the ranges, this is something we're developing at this time, trying to develop at this time. Typically, the ranges really come into play more for your micronutrients, manganese, copper, boron, etc. Because if anything is going to be limiting in this system, it's going to be those typically. And then how do you know how much is available and unavailable? That's where the next test comes in. The next test I'll mention, and I know we're running short of time, the next test I'll mention measures the available fraction of those. It's actually the Haney test that we're going to discuss. And Dr. Haney and I have been running the same soil for total nutrient digest and Haney test and looking at the relative health of those soils. And we're going to be presenting graphs and things showing you that in soils that are relatively unhealthy by a lot of other metrics, the proportion of nutrients are unavailable. And most of them are always in the unavailable form, honestly. But as your soil gets healthier, those proportions change. In other words, the Haney test extracts more phosphorus as the soil gets healthier because more of it is in flux. Because as your biology increases, then that's where we see more availability of these nutrients. So that's a great segue right into the Haney test. And I know we're a little short, Felicia. I hope it's okay if we run over just a little bit.
It is.
Understand if anybody's got to go, I apologize. It's supposed to be an hour. I'm long-winded. So the Haney test is taking a slightly different approach to this approach. So traditional approaches to soil testing were let's measure quote unquote plant available nutrients using different extracts, right? Different chemistries. We're going to measure soil pH. We're going to measure soil organic matter. The laboratory takes that information, or your agronomist or yourself takes that information, and you make fertility recommendations based on the crop you're going to grow and the demand, the yield that you're hoping to get. The issue here is that it's completely focused on chemistry set. Even organic matter in this context is discussed as in the world of chemistry. Anyone who's looking at this says their question is, well, how much nitrogen credit do I get to take from my organic matter? Well, the problem with that is that as soon as you take nutrients out of the organic matter, you no longer have organic matter. You have to destroy the organic matter to do that. It's like making a cake and then saying, all right, I want to take the eggs back out of the cake. Well, if you can deconstruct the cake, that's what the microbes are going to do, and get the eggs out, you no longer have cake. And so most growers I've ever talked to, they tell me they do not want to lose organic matter. If anything, one thing that they always tend to agree on is they're trying to increase soil organic matter. And it's one of the very few things that almost every grower I've talked to, hands down, has said, I want more organic matter in my soil. So we have to take a little bit of a different approach. The test was developed by Dr. Rick Haney in Temple, Texas. That's why I call it the Haney Test. I've been running this test for about 14 years. I'm actually finishing up my PhD dissertation on this test. To date, we have analyzed almost 250,000 of these. 48 different states, or 49 states out of the 50, 38 different countries. They come to us from all over. Rick's philosophy here was, he sat back as a PhD soil scientist and chemist, soil chemist, originally, saying, well, look, nature grows a skin for living systems. In agriculture, we call those skins weeds, but it's Mother Nature trying to grow something to cover bare soil. Native systems cycle nutrients. They are very diverse. There's no monocultures present in nature. If you see a monoculture, it's because we've influenced it to be there. Yes, you can have dominant species in an ecosystem, but if you really look, through the trees at the forest, you'll see lots of other things there, right? Mother Nature seeks balance. Our bodies do this, temperature regulation. The carbon to nitrogen ratio of soil organic matter is the same, whether you're in Brazil or Alberta, Canada, or anywhere in between. It's because Mother Nature creates that balance. Highly integrated, incredibly integrated. The butterfly effect is real in Mother Nature. Extensive R&D experience. And the reason he's mentioning that is he's saying, we as a species have a little bit of an ego, some of us more than others, maybe me included, but we think that we can control everything and technology will answer all the questions. He's saying, look, mycorrhizal fungi associations, symbiotic relationships, these are things that have been developed over millions of years. Designed by a high power, etc., whatever you believe, but it's not us. We didn't do this. So pay attention to those types of systems. Plant root networks, we think plants don't communicate or help each other, but they certainly do. And it's important to keep that in mind as plant roots communicate with the soil extensively. So the approach that he's taking is, we're going to still measure nutrients. We're still going to measure chemistry, NPK, but we're also going to measure organic nitrogen and phosphorus. And when I use the term organic, I don't mean organic OSHA, or excuse me, not OSHA, but organic certified fertilizers. We're talking about nitrogen tied to protein, or in the form of protein or amino acids in the organic form. Phosphorus that's tied into organic molecules, not just free phosphate. We're going to look at microbial biomass a little differently than respiration. And we're going to also look at water extractable organic carbon and carbon to nitrogen ratios. So really quickly, how do we extract this nutrient? Well, the extraction that was developed is called H3A. And the extractant is designed to mimic soil solution. So it uses organic acids that plants produce as root exudates. What those exudates do is they temporarily change soil pH. Now, on a micro scale, think of like a micro size. And that helps increase nutrient availability for certain crops, or certain nutrients like zinc and manganese and iron, which are driven by pH. The philosophy here is that most extracts that the lab uses involve chemistry that your soil never sees in real life. In other words, we're using chemistry that was developed in a lab. It's full of acids like hydrochloric acid, nitric acid, sulfuric acid, low pH stuff, high salts, lots. I mean, they're very strong. You don't want to get them on you. And then we say, well, this is supposed to tell you what's plant available. Dr. Haney says, well, it doesn't rain Malic 3 solution. We don't irrigate with Malic 3 solution. Plants don't produce Malic 3 solution, and microbes don't produce Malic 3 solution. So why do we use Malic 3 solution to evaluate nutrients? Not here to argue which is right or wrong. It's just a difference in philosophy. I happen to side with this philosophy more. Yes, we run all the other tests too. But from a soil health perspective, this is the side we like to go with. In this extract, this is what is in it. It's really weak. It smells like Tang. For anybody old enough to remember the orange astronaut drink Tang, that's exactly what it smells like. And that's because Tang also contained all three of these things in addition to some other ingredients. From this, we measure all of these things: plant available nitrate, ammonium, phosphate, etc. And then we measure total extractable phosphorus. That allows us to calculate organic phosphorus. So total extractable phosphorus minus the plant available phosphorus gives us this gap. And that gap is phosphorus that's available, it's soluble, it's available to the microbes, but it's not in a form that's yet available to the plant. And so guess what the microbes do? When the plant calls for phosphorus, the microbes are converting phosphorus from that pool to make it plant available. Why would they do that? Well, because the plant is giving the microbes the one thing it wants more than anything else, which is carbon. So the microbes want carbon. It's a trading system. And they do the same thing with nitrogen. So these microbes doing this work, we measure these through respiration. So this is the actual instrument that we use. It's an instrument that I actually build, designed by Rick Haney originally, the prototype. It uses infrared gas analysis. We use this to replace Solvita. Solvita paddles had their purpose, but they're just too expensive and too variable. It's a colorimetric measurement. This is a direct measurement of gas. So the way this works is we do a dry soil. We try to mimic the re-wetting and drying cycles that happen. And I know for people that are in dry environments or in a drought, they say, well, it's always dry, you know, and it's not. The microbes are adapted to this. They've dealt with this for millions of years. Droughts happened before us. They just happen to seem a little more prevalent recently than normal. But what happens when you take a dry soil and add water to it? The microbes have this flush of activity. We are optimizing moisture and temperature in the lab because we want to maximize that flush, and we capture that as a representation of microbial biomass. The larger the flush of activity, or the larger the flush of CO2, the more microbes are there. And so that's really what this is measuring, is biomass, and it relates to activity. The more microbes you have, the more active the soil can be in general when conditions are right. So there's a whole lot of words here, but this is just showing you what this one number from this test can tell us regarding implications on management. This is not an extensive list. This is just a list of ones I put together. If we just look at the two extremes, so, you know, very little potential for microbial activity because we have such a low biomass. What you might see, well, or not see, but what the soil may exhibit is slow nutrient cycling and residue decomposition. So in this scenario, if you're seeing high carbon residue last 2 to 3 years or more, this is an indicator, especially if your respiration's low, that, okay, we don't have the biological activity, the capacity to cycle nutrients. What this means from the Haney test is that we give very little nitrogen credit from the organic in pool, which we'll talk about in a minute. In other words, there's not enough microbes doing enough work to cycle nitrogen through the system. These systems are almost 100% reliant on nitrate and ammonium fertilizer. On the other end of the spectrum, these are the people that have a hard time keeping residue on the field. These are the people that have wheat straw breaking down in 4 weeks, 5 weeks, that type of thing. Really high potential for nitrogen cycling and nutrient cycling in general. And we usually maximize those credits from the test when we're giving those to producers. The challenge that you may have in this situation, of course, is how do you keep feeding the system, right? How do you keep the carbon high enough to feed that system? So this is just from that one number respiration. We then are going to couple in organic nitrogen and phosphorus and water extractable carbon. And I put those together because they're highly interrelated. The way we do this is we use water as an extract. So we use H3A with the plant root exudates to look at nutrient availability. We're using water, just deionized water, to look at the availability of soluble carbon, total nitrogen, soluble total nitrogen, which includes nitrate and ammonium, and then again, this organic fraction. We see another carbon to nitrogen ratio here. This is different than the carbon to nitrogen ratio of your cover crop. This is the transitional carbon to nitrogen ratio going from residue to soil organic matter. We calculate an organic nitrogen release using the microbial biomass and these metrics here. And ultimately, you get a soil health score. To be real honest with you, the soil health score is probably the least meaningful number on the Haney test, but Rick developed it because everybody likes a single score. And so the single index or score combines several of these different numbers to spit out a final score. We use water in this instance. I mean, I asked Rick Haney this 15 years ago as a naive person working in a lab, and I said, why water? It seems too simple. And his very academic, simple response to me was, well, last time I checked, it rained water. And so, you know, it sounds incredibly simple, simple-minded, you know, to use water, but he's looking at what is taking place in Mother Nature. Well, it rains, water. Yes, the water mixes with the soil and it's not pure water, but water is the primary constituent of soil solutions. So we're using water to evaluate what the microorganisms have access to and what they can see. So a quick note about carbon. Soil organic matter is the quantity of organic carbon. If your soil organic matter is 2%, the organic carbon is about 1.2%. Water extractable organic carbon is the subset of organic matter that's actually available. It's the soluble fraction. This is the food that drives the soil microbes. So water extractable reflects the quality. So for example, I've measured many soils with organic matter at 1.2% sand. The water soluble fraction is 400, 500 parts per million. In comparison, we measured lots of soils from the upper peninsula of Michigan and that Minnesota, organic matter 8%, water soluble carbons less than 150 ppm. Great big house, huge house, no food in the house in that scenario. And we see that reflected on respiration. So how does nitrogen play a role in all this tied to carbon? Well, this is a general nitrogen cycle. You can Google them. You'll get 1,000 responses, images. But nitrogen is constantly in flux. That's what makes nitrogen management so hard or so difficult. But nitrogen is constantly being shoved into organic matter and released from organic matter. Ammonium is the middle step. Ammonium is what the plants prefer to take up because it's closer to a protein than nitrate is. However, in the presence of oxygen, ammonium quickly gets converted to nitrate. And so nitrate is what we generally start with. Nitrate, we have an extreme risk of loss through denitrification or volatilization, and also leaching, depending on your environment and soil texture. So what we're going to measure here is we're going to measure inorganic nitrogen, plant available forms, nitrate and ammonium, just like a conventional soil test. Because nitrate is soluble, we get the exact same numbers. We should. And then we also measure water extractable organic nitrogen, soluble protein. So when you feed organisms or livestock, one of the first things they digest is soluble protein. Microbes also want to digest soluble protein. Again, they want to eat steaks. They don't want to eat nitrate. So if they're using nitrate, there's something wrong in the soil system. So this is that pool of N that's available to the microbes. It comes from soil organic matter. It also comes from cover crop and plant residues, manure, compost teas, etc., etc. Yes, it is water soluble, but it has a lower risk of loss compared to nitrate and ammonium, simply because if the protein and nitrate are both present in the environment for a microbe, which one do they attach to? Which one do they go after? They go after the protein. In other words, they're trying to catch the big fish, and the nitrate sits over on the sidelines and it can move a lot faster. So organic nitrogen is literally the safety deposit box for your soil's nitrogen. When you apply nitrogen fertilizer, if you really want to make it not leave your system, tie it up in a crop, right? Even if that's a cover crop, you tie up nitrate because the crop takes nitrate and makes protein. When that residue is returned to the soil, the microbes, it's locked up in a little vault, and the microbes have the combination to get that out. So that's how you increase nitrogen use efficiency, by increasing this cycle. How do we get it out, and what plays a role in that? The carbon to nitrogen balance of the food. So again, this is the carbon of the food they're eating and the protein of the food they're eating. If the microbes are eating rice cakes, really high carbon, low nitrogen, they do not release nitrogen back into the soil environment. They tie that up. Microbes need nitrogen too. However, if they're eating a high protein food source, ideally between 8:1 and 15:1, they will mineralize or release nitrogen. We know this, we know this, we've seen it. Any of you familiar with livestock, if you feed cattle wheat straw, really high carbon, low protein, we generally supplement with protein, don't we? To make that a more balanced ration, because the cattle don't perform as well, the composition of the manure changes. However, if you feed them pure alfalfa, we have to supplement with high fiber or high carbon feed because the composition of the manure changes, and that's where you never want to be on the back end of a cow within 30 feet, right? This process is what we do. It's what all organisms do. Microbes are doing it as well. This changes what they return back to the plant. So again, another table here, you're going to get these slides. I'm not going to go through all this, but this is kind of the different result on the left and how we would rank those. And then the nitrogen implications regarding those ratios. Again, too high, tie up, too low. Yeah, you can release nitrogen, but you got to have energy to do that as well. I always joked around that, I've got 2 young children, and the first time dad was responsible for feeding them breakfast, I joked and I said, yeah, I gave them Coca-Cola and Pixie Sticks. I didn't. Don't call Department of Health and Human Services. But what's the problem? They loved it. They ran around the house full of energy, bouncing off the walls, right? Well, it's all sugar and it's all energy. No nutrition, no protein, no anything. So then at the same time, you say, well, I can fix that. We'll just give them Flintstone vitamins for breakfast. Well, that's all nutrition, no energy. It's balancing those two things is what drives this system. So from a management perspective, you're trying to balance that system. If this is out of whack, you can change what you're planting in your cash crop rotation. You can change your grazing habits. You can change your cover crop mixes, etc. There's a lot of ways to address this, but this is the first step. Finally, we get to the soil health calculation. I mentioned this. It's important, but it's not anywhere near important as a lot of these other numbers. But in general, lots of questions on this. This is how it's calculated. It's soil respiration divided by 10 plus the water extractable carbon divided by 50 and the organic nitrogen divided by 10. These are weighted based on their importance. In general, we like to see, the higher the better, right? This is one of those scenarios, the higher the better. What's the highest one I've ever seen? From a soil standpoint, it's around 40. Yes, people test compost and manure and they're really, really high, but the 7 is a good place to start. Everyone says, what should the number be, right? Well, from the soil data itself, when we get to the point of 7, that's where we start to generally see benefits to soil structure, nutrient cycling, residue decomposition, nitrogen availability. We really like to see it above 10. Now, keep in mind, environment has an influence, right? What's your potential? Well, everyone thinks Gabe Brown in North Dakota has the highest soil health scores ever, right? Just what everyone asks me, why he's the highest. His soil scores around a 25 to 28. But yet we've got soils in Pennsylvania and Ohio scoring 36. And so he's limited by environment. 13 inches of precip a year, maybe 11. Most of it is snow, cold, etc. So there is a context there. And we've run enough of these. I have a pretty good idea of different potentials. So if somebody told me I'm in this location, I've got enough data to say, well, realistically, 17 is kind of towards the top end of your potential, right? I'm not saying we can't beat the potential. It's just set realistic goals, right? This is what a Haney Test report looks like. There are about 56 different numbers on here. Again, we offer a PDF telling you what each of these things are, and I'll send that to Felicia as well. We also have a 9-page interpretation guide that goes through not every number on here. We don't discuss pH directly or nitrate because those are things people generally know if you've done any kind of soil testing. But we do discuss the seed-N ratio, percent max, some of these other numbers on this report that are going to look very different to you. Those tables are also provided in the interpretation guide, etc. But you can see here, nitrogen. Nitrogen is the very first thing on this list. There are 9 different numbers presented to you for nitrogen. Most soil tests give you 2, and it's parts per million nitrate and pounds per acre nitrate. This test has got 9. Phosphorus, we've got 6 different numbers here. You're still getting pH, buffer pH, soluble salts, excess slime, soil organic matter. Those are run exactly the same way as other tests. You've got fertility measured through the H3A extract, zinc, iron, manganese, copper, magnesium, etc. We do not calculate CEC and base saturation on this test. And the reason is because different extracts give you different results for nutrients like potassium. If we start calculating CEC, you're going to wonder why your CEC is so different than what you've seen before. If you've ever run a conventional test, you're going to wonder why your base saturation looks so out of whack because sodium is soluble. So we get the same number on this extract as we do other extracts. But potassium is not soluble. So H3A gives you a lower number. So when you start doing percentages, it makes it look like sodium is really high compared to calcium, magnesium, etc. I'm happy to answer questions on that in an email or something too, but it's just the reason we don't include that. Soil health, you've got soil respiration. This is your microbial biomass. There's your water soluble organic carbon, and percent MAC is just the relationship between carbon availability and how much the microbes are spending carbon through respiration. It's a percentage. There's your C to N ratio. That is not 10 to 94. It is 10.94 to 1. Yes, these are very sensitive tests. We're able to exhibit the ratio with decimals. The soil health score is SHC. Again, sorry, we had to abbreviate a lot of this on the report to get it all on here. We offer you a cover crop suggestion from, this is not a species suggestion. This is just a grass to legumes and brassicas ratio mix. Because we run samples from all over the world, seed availability, equipment availability, rotation, all those things influence what you will plant from a species standpoint. That's not something the lab can really help you with there directly. We also show you this nitrogen comparison. Really interesting. So traditional nitrogen is just looking at nitrate. Most soil tests only measure nitrate. So that's your pounds per acre credit. The Haney Test nitrogen includes nitrate, it includes ammonium, and it includes organic nitrogen release from the microbes. The difference is simply the difference between the two. So in this example, the conventional test would have given you a soil credit of around 45 pounds. The Haney Test is giving you a credit of around 122 pounds for a dollar savings of around $80, depending on what price of nitrogen you're paying. Now, just because we're showing you the difference doesn't mean that you have to absolutely reduce your in-fertilizer rate by 80 pounds. That, you know, for most people, that is really not in their comfort zone. But it may give you some confidence that you can cut back 30 pounds and see what happens, right? And if that works well, then you continue down that path. And that's where most people are using this test. It's to save on nitrogen fertilizer. Sorry, I guess I had these blocked out just to show you in bigger format, but it's the same things I just covered here. And that nitrogen comparison. And then the last slide here, I believe, is just in general, the sampling how-tos. There's not a lot different with sampling. We recommend a 0 to 6 or 0 to 8 inch depth. You can use other depths, but you got to let us know what they are. 10 to 15 cores per sample, so you composite those together to mix them up. We're not grid sampling in this program for these. You're taking a composite average of an area of interest or a field. Just keep them relatively cool, out of direct sunlight. Don't throw them on the dash of your pickup or in a box in the back or something like that. You can use a plastic freezer bag. You can represent up to around 40 acres. Now, again, that's dependent. We have fields up here that are 600 acres and they're all flat tabletop, same soil type. You can go beyond 40 acres, but on average, it's around 40. We do recommend that you wait for soil temperatures to be around 50 degrees. For some of our northern neighbors in Canada that send us soil samples, that is not really obtainable. It's okay to soil sample when it's cooler than that. But again, consistency is key. We had individuals pulling soil samples when the temperature was 70 degrees, and then they would want to compare those to soil samples pulled at 35 or 40 degrees, and it's too big of a gap temperature-wise, too different of a season. When should I do this? Well, like the other tests, just before making big management changes, once per year or every other year, and you want to track change over time to look at soil health. If you're using the Haney test for nutrient management, especially nitrogen, then you want to pull the test prior to fertilizer application. So if you terminate cover crops in the spring and you're going to apply in the spring when you plant, pull a soil sample at the time you're going to terminate cover crops. It's a great idea to pull a cover crop sample at that time as well. We integrate those two tests together to manage your nitrogen credits. If your goal is to reduce input costs, conventional soil tests are not designed to help you reduce your input costs. They're just not. Originally, that was the idea. but somewhere along the lines, most conventional soil tests got adopted by fertilizer companies as a wonderful marketing tool to sell you fertilizer. I am not against fertilizer. I just don't understand why we're recommending 1.2 pounds of nitrogen to produce a bushel of corn. When you remove a bushel of corn from your field, you take 0.7 pounds. So where is the other 0.5 that you paid for? And if you're growing 200 bushel corn, that's 100 pounds of extra nitrogen that you applied that is somewhere, right? And they say, well, you lost it to the atmosphere, you lost it to the water table. Well, if that's the case, then we need to start figuring out how to stop losing it, because nitrogen fertilizer is not free and it's not getting cheaper, right? So that's the goal, the drive behind this. It's not to eliminate fertilizer. Nutrients are important. The microbes don't care if they prefer protein, but they don't care where their phosphorus comes from. If you take phosphorus and put it on a corn crop, that's a conventional corn crop. But if you harvest that corn crop and feed it to a cow and then scoop up the manure and apply that to the next corn crop, that's an organic corn crop, right? I mean, so the phosphorus that went all the way through the system is the same. The microbes don't care, okay? If you're putting on fertility every year, then obviously we sample once a year. Again, no reason to sample more than that. So again, I know that I blew through the hour, Felicia, but I hope that wasn't too overwhelming for everybody. And I will get the slide deck and the interpretation information over to Felicia. And I see we have one other question here really quick. First time farmer here. Thank you for your presentation. You're very welcome. Some parts were advanced for where I'm at in terms of what each test means and the numbers on it mean for my soil and operation. I completely understand that. And I do apologize. I wasn't trying to talk over anybody. I do a lot of these presentations in person as well. And I can tell you that every time I've got a third of the room says, I was so lost. I don't even know what any of that is. I've got a third of the room that's kind of like, yeah, that was just right. And I've got a third of the room going, that was boring. How come we didn't dive into this more or that more? So I do apologize. It's a very hard thing to do, but please feel free to use my contact information, send me an email. I'm more than happy to talk about it in the context of where you are. So with that, I guess, thank you, everybody. I'll turn it back over to Felicia.
Thank you so much, Lance. We appreciate this information. I want to briefly, if you look at the chat, I have information in the chat, but want to thank everyone for joining us today. And this is a NRCS Piney Woods project entitled Racial Equity and Justice Conservation Project with NCAT and Up and Farms. So definitely the slide deck will be sent to me and other information. So please reach out to me if you would like that information, as well as this video will be on the NCAT ATTRA YouTube channel within possibly a couple of weeks. So give it a chance to get there for you to review. But thanks everyone for joining us today. If you have any other questions, please reach out to Mr. Lance or I, and I definitely could get it to him to answer your questions.